I welcome you all in this lecture of the numerical methods. In my previous lecture, I have given you the definition of rate of convergence and order of convergence, and then I have given you the rate of convergence of the bisection method. Now, in this lecture, I will define the rate of convergence of the Regula Falsi method, Secant method, and then Iterative method. So, let us start with the order of convergence of this Regula Falsi method and Secant method. Order of convergence of Secant method. First, let us discuss the rate of convergence of the Secant method, and then we will discuss the rate of convergence of the Regula Falsi method. So, let A is the exact root of this equation fx equal to 0. Now, if it is the exact root, then it will satisfy this equation. So, our fa will be 0. Now, let us assume xn plus 1 equal to a plus en plus 1, where your en plus 1 is the error at the n plus 1 iteration. Your xn as a plus en and your xn minus 1 equal to a plus en minus 1. Then using the formula for this second method, we have xn plus 1 equal to xn f of xn minus 1 minus xn minus 1 f of xn divided by this f of xn minus 1 minus f of xn. Okay, now let us put the values of xn plus 1, xn and xn minus 1. So in the left hand side we have a plus en plus 1. Now in the right hand side we have a plus en. Then we will have f of a plus en minus 1. Then we have a plus en minus 1. Then we have a plus f of a plus en. Now in the denominator, your fxn minus 1 means your f of a plus en minus 1 minus f of a plus en. Okay, now if you multiply this equation by this term by a, then this will be your a times f of a plus en minus 1, and here we will have a times f of a plus en. And if you take a common, then you can see that this term will get cancelled with the numerator. So this is equal to a time, then this is your en times f of a plus en minus 1, then we will have en minus 1 f of a plus en divided by this bracket f of a plus en minus 1 minus f of a plus en. Okay, now this a will get cancelled with the left hand side, so we have en plus 1 equal to, so here we have en plus 1 equal to en f of a plus en minus 1 minus en minus 1 f of a plus en divided by f of a plus en minus 1 minus f of a plus en. So this is our error at n plus 1 iteration. Now let us apply the Taylor's theorem. So after expanding this term or this fa plus en with the help of Taylor expansion, we have en. Now let us use the Taylor expansion. So we have f of a plus en minus 1 f dash a plus en minus 1 whole square upon factorial to f double dash a, then we will have the higher order terms. Similarly, this en minus 1 f of a plus en f dash a plus we will have en square upon factorial 2 or f double dash a, and then again we will have the remaining higher order terms. Then this is divided by, again expand the denominator with the help of this Taylor expansion, So we have f of a plus f dash a into en minus 1. Then we will have en minus 1 whole square upon factorial 2 f double dash a, and then the higher order terms. Then we will have minus f of a plus epsilon, so which is equal to f of a plus en f dash a. Then we will have en square upon factorial 2 f double dash a, and then the higher order terms. Okay. Now, as your a is the exact root of the equation fx equal to 0, so this fa and this fa will be 0, and again this fa is 0. Now, this en into en minus 1 of f dash a, and here the en into en minus 1 of f dash a will get cancelled with each other. So, now in the numerator, if you multiply this en to this term, then we will have en into en minus 1 whole square upon 2, and here we will have en minus 1 into en whole square upon 2, and you can see that your f double dash a is common. So, now after subtracting the numerator, we will have the terms like this: en into en minus 1 whole square upon 2. Then here we will have en minus 1 into en square upon 2. Then at outside we will have f double dash a. And again, after that we will have the terms of order cube. So I can write those terms like this: order of en cube. So after that we will have the terms of order 3. So this is your numerator, and here you can see that this fa and fa is cancelled. Now if you take this f dash a common, then we will have en minus 1 minus en into f dash a, and then here you can see that this is your, if you take this f double dash a common, then again this is your en minus 1 square minus en square into f double dash a upon 2, and again we will have the higher order terms. Okay, now if you take en into en minus 1 by 2 common, then in the numerator we will have en minus 1 minus en, and again if you take en minus 1 minus en common, then this numerator will get cancelled with this en minus 1 minus en. So this is equal to, okay, just write, okay, this is equal to, now this term will get cancelled. So now in the numerator we will have en into en minus 1 upon 2 into f double dash a plus the order of en cube. Now here we will have, now this term is cancelled, so we have f dash a plus, now here we will have en minus 1 plus en into f double dash a upon 2, then again we have the higher order terms. Now here we will have the order en square, as we have taken this term common. If we neglect this cube and here this is square, then this is approximately equal to, this en is at the nth iteration, so its cube will be very small, so we can write it approximately equal to, so your en plus 1 is approximately equal to, now this is your en into en minus 1, en into en minus 1 into f dash a divided by 2 times f dash a plus, again this 2 will come here, so we will have en minus 1 plus en f double dash a. Okay. Now if you take this term common, this f dash a common, then this is equal to en into n minus 1 f dash. In the numerator we have f double dash a, so this is your f double dash a divided by 2 f dash a. Now this bracket will be your 1 plus this en minus 1 plus en f double dash a upon 2 f dash a. Now if you take this term in the numerator, then we will have 1 plus en minus 1 plus en f dash a upon f double dash a upon 2 times f dash a, and the power is minus 1. Okay, now after expanding this bracket with the help of the binomial extension, then this will be 1 minus x, and we can write it approximately equal to, again this is your 1 minus x, and I am not going to multiply this x with this bracket because that will give you ultimately the higher order terms. That means that will give you the en square or en minus 1 square. So I am neglecting the higher order terms. So this is approximately equal to en into en minus 1 into f double dash a upon 2 times f dash a. So therefore en plus 1 we can write it approximately equal to, say this is your some constant a. Say this is your some constant a, then this en plus 1 is equal to a times en into en minus 1. When my a is equal to, your a is equal to f double dash a upon 2 times f dash a. So this is equation number 1, because we will need this equation for the convergence of Regula Falsi method. Now here we have en plus 1 equal to a times en into en minus 1. This is when we have taken the interval, when we have taken our xn plus 1, xn and xn minus 1. Okay. Now, if suppose that lambda is the asymptotic error and small p is the order of convergence, then by our definition of the order of convergence, by definition, we have en plus 1 equal to lambda times en power p. Again, this was your approximately equal to this value, where your lambda is asymptotic error and your p is the order of convergence, where your lambda is the asymptotic error and p is the order of convergence. So let us find the value of en minus 1 with the help of this expression. Say this is your equation number 2. Now, okay, just write this value here. So this is, from here we can see that our en, from here our en will be equal to, if you find the value of en from here, then your en will be equal to en plus 1 upon lambda power 1 upon p. Now again, your value of en minus 1 will be equal to, take this lambda power 1 by p in the numerator, so we will have lambda power 1 minus p and into en plus 1 power p. So this is the value of en minus 1. Now just put the value of en plus 1 and en minus 1 in this equation number 1. So by 1, your en plus 1 was lambda times en power p, and in the right hand side we have a times en, and then the value of en minus 1 is, then here the value of en minus 1. So if you replace your n by n minus 1, then this will be your en. So the value of en minus 1 is equal to lambda power minus 1 by p into en power p. Okay. So here we have 1 by p. So this is your 1 upon p. So again this is your 1 upon p. Okay. Now let us take this en power p in the right hand side, then or you can combine this en and this en power 1 by p. So we can say that our lambda, and in the left hand side just take this minus 1 upon p here, then in the numerator we will have lambda power 1 plus 1 by p, now into en power p equal to a times this en power 1 plus 1 by p. Now if you equate the powers of both sides in case of en, then you can see that equating powers of en we get p equal to 1 plus 1 by p. Also, we will have a equal to lambda power 1 plus 1 by p. So from here we can have the value of lambda, which is your asymptotic error, and your a was this value. Your a is this one. So with the help of this a, we can have the value of this lambda, which is your asymptotic error. Okay, now on solving, this is equal to p square. Now this will be your minus p plus 1 equal to 0. Now this is equal to p equal to minus b plus minus b square minus 4ac. So this is equal to p equal to minus b plus minus b square minus 4ac. So again this is your minus 1 upon 2a. So this is equal to 1 plus minus root 5.2. Now if you take the plus sign, if you take the positive sign, then we will have 1 plus root 5.2, 3.236 divided by 2. So from here we get p equal to 1. So this is your 1.6. So this is your 6, then we will have 1, then we will have 8. So your p is equal to 1.618, which is more than the order convergence in case of linear convergence. Now again, this is your order convergence, and your rate of and your asymptotic error can be obtained with the help of this lambda. Okay, now what is the order of convergence of the Regula Falsi method? So let us discuss the order of convergence of Regula Falsi method. Again, we have a common term, similar steps. Again, adopting these similar steps for this Regula Falsi method, we will get this equation number 1. Now, with the help of this equation number 1, we can guess the order of convergence of this Regula Falsi method. So again, proceeding in a similar way of second method, proceeding in a similar fashion manner to second method, we have this En plus 1 equal to a times En into En minus 1. We have obtained this result here, which was your equation number 1. So we have this equation here. Now what is the difference between second method and Regula Falsi method? In second method, we do not require this type of condition for successive steps, for successive iteration. So as we do not need this type of condition, so we have a iterative formula, which is your xn plus 1 equal to xn into f of xn minus 1 minus xn minus 1 of fxn divided by f of xn minus f of xn minus 1. Now this is your fixed for second method. Now in case of Regula Falsi method, our interval gets changed. For example, in the initial step, suppose that our root is between a and b. Then in the second step, if the first iteration is x1, then your root can be between a or x1 or b or x1. So in Regula Falsi method, our one end of the interval, one point of the interval will remain fixed. I have already shown this in my previous problem when I was solving the problem based on this Regula Falsi method. At that time, I have shown that in Regula Falsi method, one of the end point of the interval will remain fixed. So, as in Regula Falsi method, that means if this is fx equal to, say, this equation. Now, suppose that your f of 0, here you can say that this is your 1, your f of 1 is, now your f of 1 is again 1, and your f of 2 is plus, and if you take x minus 1, if you take f minus 1, then this is your minus 1, again this is your minus 1, then we have this one as equal to minus 1. So that means our root will lie 0 and minus 1. Now in this regular Falsi method, our first iteration will be x1 equal to, now the root will be between 0 and minus 1. Then our root will lie between either 0 and x1 or minus 1 and x1. Again in the second step, our root will lie between either 0 and x2 or x2 and minus 1. So that means either the endpoint 0 or the endpoint minus 1 will remain fixed. So in regular Falsi method, one end of the one end of the enclosing interval always remain fixed. So in regular Falsi method, one end of the enclosing interval always remain fixed. If x naught is such endpoint, then in this regular Falsi method our curve will be replaced by a chord. Then in regular Falsi method, our curve fx will be replaced by a chord joining this x naught comma f of x naught, and suppose that at another step we have this value. So here as our x naught is the one end point which is always remain fixed, so our root will lie between these two points. In this case, our en plus 1 will be equal to a times, now this is the corresponding value for this x naught will be your a e naught, and the corresponding error for this xn will be your en. As our x naught is fixed, so that means this value is your constant. So here we can write en plus 1 equal to this says c into en. As our x naught is the fixed point, so this e naught will be fixed, a is the constant, so we have this value as c into en. Now here you can see that your en plus 1 is directly proportional to en power 1, so your order of convergence is 1. So in this case for p is equal to 1, so the order of convergence of this regular Falsi method is 1. So the order of convergence for the second method is 1.618, whereas the order of convergence for this regular Falsi method is linear, that is your 1. And that is because our one end of the enclosing interval always remain fixed, and that is why we have this type of condition. And as this e naught is always fixed, so we can write this as a constant, and here we have this en plus 1 equal to c into en power 1. So your order of convergence for this regular Falsi method is equal to 1. Now I will discuss the condition of convergence of the iterative method. Then we will find out the order of convergence of the iterative method, and if the time persists, then I will discuss the order of convergence of Newton-Raphson method. So let us discuss the order of convergence of this iterative method. Condition of convergence of iterative method. Condition of convergence of iterative method. Let us suppose that in iterative method our sequence converges to a exact value small a. let our sequence say xk converges to an exact value small a of the equation fx equal to 0. Now this equation fx equal to 0 can be written as, now in iterative method or in fixed point iteration method, we can write this fx equal to 0 as x equal to phi of x. So from here we have this a equal to phi of a, as our a is the exact root. So as our sequence is converging to a, so we will have a equal to phi of a. Okay, again, if x naught is the initial approximation, you can obtain this x naught basically with the help of a graph. So if this x naught is the initial approximation, then our first iteration x1 will be equal to phi of x naught. So this x1 minus a, so this implies that your x1 minus a is equal to phi of x naught minus phi of a. So this is your xn minus a. Now we know that the mean value theorem. In mean value theorem, if the function f is continuous in the closed interval a comma b, and suppose that it is differentiable in the open interval a comma b, then there exists a point c between a and b for which we have this condition fb minus fa upon b minus a, and you can see that this is your slope. This is your slope joining the 2 points of the curve. So with the help of this mean value theorem, this fb minus fa can be written as b minus a into some f dash c, where your c lies between this x naught and this a. So from here we can write this x1 minus a equal to x naught minus a into phi dash say a1, where your a1 will lie between this x naught and a, where your x naught, where your a1 will be a value between x naught and a. So similarly we can have the value of x2 minus a. Again our x2 minus a will be equal to, this x1 is coming in terms of x naught, so your x2 minus a will be x1 minus a into some value a2, phi dash a2, where your a2 will be between x2 and, where your a2 will be between your x1 and a. Then we will have x3 minus a, that will be your x2 minus a into phi dash your a3, and similarly your a2 is between x1 and a, your a3 is between x2 and a. Similarly your xn plus 1 minus a will be equal to xn minus a into phi dash an, where your an is between xn and a. Now let us multiply all these equations. Now if you multiply all these equations in the left hand side and right hand side, you can see that x1 minus a will get cancelled with this x1 minus a, your x2 minus a will get cancelled with this term, your xn minus a will get cancelled with this previous term. So in the left hand side we will have multiplying these equations, we have our xn plus 1 minus a equal to, now our first term will be here and then the product of these 5. So we will have phi dash a1, phi dash a2, then finally we will have phi dash an. Let us take its modulus. So we have xn plus 1 minus a equal to x naught minus a into phi dash a1. Then we have phi dash a2 and then your phi dash a. Now this xn plus 1 minus a is your en plus 1. That means the error at n plus 1th step. And this is your e naught. That means the error at first step. Now let us assume that these all phi dash are less than some quantity, say c. So let us assume phi dash x is less than c, where, or you can write, let us assume that the phi dash a1, phi dash a2, comma phi dash an, all are less than c. Suppose that all are less than equal to c. So if all are less than equal to c, less than or equal to c. So we can say that now in the left hand side this is your error at n plus 1th step. So we have en plus 1. In the right hand side, now this is your en. Now as each term is less than equal to c, so this is your c into then we will have c. So this is your c power m. This is your phi dash a1, then we have phi dash a2, then we have phi dash an. So we will get c power n. Okay, we have en plus 1 is less than equal to en into c power n. Now let us assume c less than 1, because only in that case your en plus 1 will get converged. So if c less than 1, then if you take this limit, then this will converge towards a finite quantity. So this will converge only when your c is less than 1. So this implies that, so if your c is less than 1, then as n tends to infinity, your right hand side tends to 0. When your c less than 1, and c less than 1 means your derivative of phi is less than 1 for all those values of x which lies between this x naught and a. So that means whenever your value a1, a2, an lies in your interval, for that if your phi dash x is less than 1, only your this iterative method will get converged. So if c is less than 1, then as n tends to infinity, your right hand side tends to 0. Hence, our iterative method will get converged only when your phi dash x is less than 1, where your x is inside this interval a comma b. So if this x is in this interval, and for this x your phi dash x should be less than 1, only then we will say that our iterative method converges. Now, so this is the condition for the iterative method to converge. Now what about the order of convergence? So let us discuss the order of convergence. Now order of convergence of iterative method. So order of convergence of iterative method, or your fixed point iteration method. So let A is the exact root of this fx equal to 0, then again we can write x equal to phi of x. So we have a equal to phi of a. Now in general iterative method, or xn plus 1 is equal to phi of xn, where your n is greater than or equal to 0. So, in general, the fixed point iteration method gives the xn plus 1 equal to phi of xn. Now, let us subtract this a by this xn plus 1. So, from here we have xn plus 1 minus a equal to phi of xn minus phi of a. Now, this is equal to, now this will be your, okay, xn plus 1 minus a. Now, this xn can be written as phi a plus en, where your en is the error at your nth iteration. Now, this xn plus 1 minus a can be written as, so here you consider this xn minus a is en, so this will be your en plus 1, that means the error at n plus 1 iteration, and in the right hand side we have this phi a plus en minus phi of a. So we have this value. Now let us expand this right hand side with the help of the Taylor's expansion. Now if you expand this right hand side with the help of the Taylor expansion, then you can see that your en plus 1 is equal to, now your phi a plus en is equal to phi a plus en phi dash a, then we will have en square by 2 factorial 2, then we have phi double dash a, then finally your nth term, your general term, say kth term, will be equal to en power k upon factorial k, then phi ka, then we will have the higher order terms, that means the k plus 1th order term. So we can write it as O of en k plus 1. Then we have minus phi of a. Now this phi will get cancelled with this phi. So from here we have en plus 1 equal to en phi dash a plus en square upon factorial 2 phi double dash a, then the general term will be equal to en power k upon factorial k phi ka, then we will have this term. So this is your en plus 1 in this case. So this is your general term. Now with the help of this equation, we will find out the order of convergence for one point iteration method, for second order iteration method, for first order iteration method, we will find out the value of this order of convergence. Now for, okay, first of all let us find out the order of convergence for this n order iteration. For nth order iteration, now for nth order iteration, your phi dash a equal to, your phi a equal to phi dash a equal to, your phi dash a equal to phi double dash a equal to this phi n minus a is equal to 0, and your phi n a is not equal to 0. So for nth order iteration we have this condition. Now if you put these value here, then we can say that therefore our en plus 1 is equal to, now this term will remain, non-zero, so this is equal to, all other term will get 0, so we have en power k upon factorial k, then we have phi k a, then so this is your phi k minus 1 for kth order. Let us discuss this for kth order iteration. This is your phi k, and this, then we will have this en k plus 1. Okay, now let us divide this whole equation by en power k. So from here we have this limit k tends to infinity En plus 1 upon, just take the modulus, upon En power k. Now this is equal to, now if you divide this whole equation by En power k, and if you take the limits k tends to infinity, then you consider here we will have the terms of k, and that will tends towards the 0 as your k tends to infinity. So when your k tends to infinity, this term will become 0, and here in the right hand side we will have this phi k a upon factorial k. Now if you take this right hand side as lambda, then this implies that your En plus 1 is approximately equal to, say this is your lambda, so we can write lambda into En power k. So here our En plus 1 is approximately equal to lambda times En power k. So that means the order of convergence. So if your xn converges to A, then our order of, say your xk converges to A, then order of convergence is k. So for kth order of iteration, your order of convergence is k. Similarly, if you put k equal to 1, then for first order iteration, your order of convergence will be equal to 1. For your second order iteration, this order of convergence will be 2. Now, for example, in case of Newton-Raphson method, you will see that Newton-Raphson method is second order iterative method. So that means in case of this Newton-Raphson method, we will have k equal to 2. So that means our phi double dash a will be not equal to 0, and in that case you will say that the order of convergence is equal